Good morning everyone. Today I am going to present probability variables focusing on the basic problems in probability. This session is a part of probability and statistics for data science. So in this lecture we will understand fundamental probability concepts and solve basic problems step by step. So let us begin with some fundamental concepts. So first, some rules of probability. So consider events A, L and R contained in some sample space S. The rule number 1 is probability of A complement is equal to 1 minus probability of A. If L and R are disjoint, then probability of L union R is equal to probability of L plus probability of R. Rule number 3, if L and R are not disjoint, we have the inclusion exclusion principle. Probability of L union R is equal to probability of L plus probability of R minus probability of L intersection. Next, in probability, we deal with events and their likelihood of occurrence. So two important types of events are mutually exclusive events and independent events. Mutually exclusive events are events that cannot occur at the same time. Events where the occurrence of one does not affect the occurrence of the other or the independent events. So we also use basic results from set theory to derive probability formulas, so which will help us solve problems easily. So if two events A and B are mutually exclusive, their intersection is 0, meaning they do not occur together. So if A and B are independent events, then the probability of both occurring is the product of their individual probabilities. So these results are very important and are frequently used in solving probability problems. So let us solve the first problem. If the probability of an even number is 0.6, what is the probability of an odd number? So we are given that the probability of getting an even number is 0.6. We need to find the probability of getting an odd number. Since even and odd are complementary events, probability of odd is equal to 1 minus probability of the even. So which is equal to 1 minus 0.6 is equal to 0.4. So the required probability is 0.4. Consider the two events A, x is a multiple of 2 and B, x is an odd and less than 10. Suppose probability of A is equal to 0.6 and probability of B is equal to 0.25. Obtain A intersection B, find the probability of A union B. So in this problem, event A represents multiples of 2 and event B represents odd numbers less than 10. Since multiples of 2 are even and contains odd numbers, these events cannot occur together, so they are disjoint events. So therefore probability of A union B is equal to probability of A plus probability of B, which is equal to 0.85. So similarly, as like the previous problems, the following problems also follow the same. A card is taken at random from a pack of 52 cards, playing cards, and then replaced. A second card is then drawn at random from the pack. Use a tree diagram to determine the probability that both the cards are diamonds. At least one card is a diamond. Exactly one card is a diamond. Neither card is a diamond. So we first note that for a single card drawn from a pack, probability of getting a diamond is 1 by 4 and probability of not getting a diamond is 3 by 4. So in a pack we have totally 52 cards. In out of 52 cards, 13 cards are diamond cards. So we put these probabilities on the branch of the tree diagram as first card in the category of diamond and not diamond, and in the second category diamond, not diamond, diamond and not diamond. So the probabilities are obtained and the total probability is always found to be 1. So probability of both the diamonds is 1 by 16. Probability of getting at least one diamond is 1 by 16 plus 3 by 16 plus 3 by 16, and probability of exactly getting one diamond is 3 by 16 plus 3 by 16 is equal to 6 by 16. Probability of neither card a diamond is 9 by 16. Event. Apply the correct formula, simplify step by step. So the key idea is to understand clearly the relationship between events before applying the formulas. So now let us introduce conditional probability. Conditional probability answers the question, how does the probability of an event change when we have additional information? For example, if we toss a coin 3 times, the probability of getting 3 heads is calculated from the full sample space. So, but if we are told that the first toss is already heads, then the sample space reduces and the probability changes. So, this concept is called conditional probability. So, here in first question, what is the probability of 3 heads when we toss a fair coin 3 times? So, we have to find the probability of getting 3 heads. So, from the sample space, we are getting 3 heads in only one event. So, that is 1 n of e, and n of s is 8, that is total elements in the sample space, the events occurred in the sample space is 8. So, n of s is equal to 8. So, probability of getting 3 heads is n of e divided by n of s, which is equal to 1 by 8. Similarly, suppose we are told that the first toss was heads. Given this information, how should we compute the probability of 3 heads? So, the sample space is narrowed to s dash, where we have first toss is to be head. So, all the outcomes are equally likely. So, probability of 3 heads, given that the first toss is heads, the number of events occurred is, total number of events occurred is 4, and in that the first toss is head, n of e is equal to 1 by 4. So, this is called conditional probability since it takes into additional conditions. So, this is the abstract visualization along with the coin example. So, this is the formal definition of conditional probability. When A and B are events, we define the conditional probability of A given B. That is, the probability of A given B is equal to the probability of A and B divided by the probability of B, such that probability of B is always not equal to 0. This leads to the multiplication rule, which helps us to calculate joint probabilities easily. So, these are the basic problems that involve the formula of probability of A given B condition, which is probability of A intersection B divided by probability of B. Now, let us consider a practical example. A box contains bad of 4 and 6 good tubes. 2 tubes are drawn and one is found to be good. We need to find the probability that the other tube is also good. So, this is a conditional probability problem where we use given information to update our probability. So, let A is equal to one of the tubes drawn is good and B, the other tube is also good. We have to find the probability that the other one is also good. So, probability of A is equal to 6 good tubes are there, out of total number of tubes is 10. So, 6 by 10, which is equal to 3 by 5. Similarly, probability of B is equal to 4 bad tubes are there, out of total probability 10. So, 4 by 10 equal to 5. So, probability of both tubes drawn are good. Already one is drawn is good and the other one must be drawn is also to be good. So, out of 6 good items, 2 can be drawn in such a way that 6C2, and out of 10 items, 2 can be drawn in such a way that 10C2. So, probability of A intersection B is equal to 6C2 divided by 10C2, which is 1 by 3. By applying the formula carefully, we can complete and compute the result. That is, the probability that the other one is also good involves probability of B given A, so which is equal to probability of A intersection B divided by probability of A, which is 5 by 9. We already know that one tube is good. The conditional probability that the other tube must also be good is probability of B given A. So, in the next problem also, the same conditions to find probability of A given B, probability of A given C and probability of B given C involves. So, the values of all these three are found out here. Next, we move to the law of total probability. So if a sample space is divided into several mutually exclusive and exhaustive events, then the probability of any event can be expressed as the sum of the conditional probabilities over these events. So that is nothing but the total probability, that is probability where E1, E2 and so on up to En has non-zero probability of occurrence in a sample space yes, and A be any event associated with that sample space, then the probability, total probability is given by the condition P of A is equal to P of E1 into P of A divides E1 plus P of E2 into P of A divides E2 and so on up to P of En into P of A divides En. This law is useful when dealing with the multiple cases or sources. So consider 3 bags containing different proportions of red and blue marbles. So it is given that there are 3 bags which contains 100 marbles, bag 1 with 75 red and 25 blue marbles, bag 2 with 60 red and 40 blue marbles, bag 3 with 45 red and 55 blue marbles. One of the bags is selected at random and a marble is picked from the chosen bag at random. So what is the probability that the chosen marble is red? So to find the probability of getting a red marble, we use the law of total probability by considering each bag separately and summing their contents. And this final result gives the overall probability, that is probability of R equal to summation of J equal to 1 to n, probability of Bi into probability of R given Bi. So similarly in this next problem, 3 companies produce products with different defect rates. So since each company is equally likely, we again apply the law of total probability. So we calculate the weighted probability of defect from each company and add them together to get the final answer. So similarly the problem 3 also follows the same law of total probability, as we assume that both men and women are in equal numbers, that is equally likely. So we again apply the law of total probability. The next one, we come to Bayes' theorem. So Bayes' theorem helps us find the probability of cause given the observed result. So it is widely used in fields like medical diagnosis, machine learning and decision making. So this updates prior probabilities into posterior probabilities using the new information. So if E1, E2 and so on up to En are non-empty events which constitute the partition of the sample space yes, where these non-empty events are pairwise disjoint and the union of these events, and A is any event of non-zero probability, then the Bayes condition is given by P of Ei given A is equal to P of Ei into P of A given Ei divided by the total probability. So now let us move to example 1. So in this example, a factory has 3 machines producing bolts with different defect rates. A defective bolt is selected and we need to find the probability that it was produced by a particular machine. So using Bayes' theorem, we combine the prior probabilities and likelihoods to compute the required probability. So here a factory produces bolts using 3 machines, as I said earlier, A, B and C, which produces 50%, 30% and 20% of the total output, but 3%, 2% and 1% of their outputs are defective respectively. A bolt is drawn at random from the product and is found to be defective. What is the probability that it is manufactured by the machine B? So we are finding the probability of an item produced by machine A, B and C as 50%, that is nothing but 0.5, 30% 0.3 and 20% 0.2, and the probability of D given A, that is the item produced by A, the probability of it being defective. So probability of D given A, similarly probability of D given B and probability of D given C is found, and probability of B given D is found out using the Bayes' theorem, and the given item is defective, probability of it being produced by B is 0.26, is found out using the theorem. So similarly, the next problem, the content of urn 1, 2 and 3 are as follows. So it contains, the urns contain 1 white, 2 black and 3 red balls, 2 white, 1 black and 1 red ball, 4 white, 5 black and 3 red ball. So one urn is chosen at random and 2 balls are drawn. So they happen to be white and red. So what is the probability that they come from the urns 1, 2 and 3? So here let E1, E2, E3 denote the events of selecting urn 1, 2 and 3 respectively. So let A be an event of that the 2 balls drawn are white and red. So probability of E1 is 1 by 3, probability of E2 is 1 by 3 and probability of E3 is also 1 by 3. So now we are calculating probability of A given E1, probability of A given E2 and probability of A given E3. So using the Bayes theorem, we apply the result and calculate the value of probability of E1 given A is to be 33 divided by 118, and similarly probability of E2 given A is calculated as 55 by 118 using the Bayes condition. So using the Bayes theorem, we have calculated and we have combined the prior probabilities and likelihoods to compute the required probability. So this method is very useful for real life decision problems. So we have covered basic probability concepts, conditional probability, total probability and finally the Bayes theorem. So these concepts form the foundation for advanced topics in statistics and data science. Thank you for your attention.